Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am starting module 6, and in this module we will study about the buckling of plates. That is very important because many cases plates are compressed, and due to compression the member is liable to be buckled. So, today my topic will be about the buckling of the plate, and before that we must note that the thin plate equations that we have so far used and accustomed to, we neglected the in-plane forces, but when the buckling occurs there must be a force in the axial directions, that means in-plane forces must be present. So, here first the emphasis will be given to derive the equations of equilibrium of the plate including the in-plane forces, and then we will go for buckling. So, in this lecture we will discuss the concept of buckling, then we will derive a equilibrium equations of the thin plate under the simultaneous action of in-plane forces and transverse load. The in-plane forces in the derivation I will take as a tensile force which is considered positive, but in case of buckling the tensile force has to be reversed, that is it will be compression. So, just by changing this, reversing the sign of the algebraic sign of the in-plane forces, we can get the equation of buckling of the thin plate. So, then solution of some problem I will discuss. The problem I will consider today is a simply supported plate, that means plate whose all edges are simply supported and subjected to UDL, uniformly distributed load, that is the UDL, and also the plate which is subjected to a concentrated load. So, two problems I will discuss in today's class. Now, let us discuss in brief what is buckling. Now, any structural member when subjected to compressive load is liable to be buckled when certain critical value is reached. So, when the critical value is reached and just it exceeds, the member suddenly bows out sideways. This bending gives rise to large deflection, which in turn cause the member to collapse. So, buckling we can understand that is a condition when the instability arises. So, that is a bifurcation problem. So, load at which buckling occurs is thus design criteria for many compression members. Now, the buckling phenomenon is understood by a paragraph that is written in a book by Salvadori and Heller. The name of the book is Structure in Architecture. So, he has explained very nicely what is buckling. So, buckling is seen in column as well as in the plate also. So, the paragraph from his book is quoted and I am reading this paragraph, then you will understand the inner meaning of this these statements. Okay. A slender column shortens when compressed by a weight applied to its top, and in so doing lowers the weight's position. The tendency of all weights to lower their position is a basic law of nature. It is another basic law of nature that whenever there is a choice between different paths, a physical phenomenon will follow the easiest path. Confronted with the choice of bending out or shortening, the column finds it's easier to shorten for relatively small loads and to bend out for relatively large load. In other words, when load reaches its buckling value, the column finds it easier to lower the load by bending than by shortening. So, this is a nice quote from this book. That means, it is a basic law of nature. When there is a load put on the top of a column, that it resists the load by lowering its position, that means it is compressed. But if you go on increasing the load, at certain point the member will be no longer to resist the load by just by compression. So, it now requires the load to be resisted by slightly by bending in a slight manner. That is, bending will generate the large reflection in that case, and the member will choose, instead of the shortening, the bending is the easiest for the member. So, therefore, the buckling phenomenon is understood as the transition from straight configuration to the bend configuration. This transition point we have to determine, and this is nothing but the critical load. So, plate is also not exception. So, there is also the chances of buckling in plate when subjected to in-plane forces. Now, there are certain difference between the plate buckling and column buckling. However, let us examine the three equilibrium positions that are important to study the buckling phenomenon. Okay. Buckling load is the limiting load under which the compression in straight configuration is possible. So, it is a limiting load up to which the members remain straight, and just increase of load above that or beyond that will lead to an unstable configuration. So, the column will now then bend, and this bending will produce the large deflection. So, it is assumed that transition from the straight to bend configuration at the buckling load occurs, because the straight configuration no longer remains stable under the action of the load which exceeds the limiting load. So, the concept of stability can be explained by considering the equilibrium of a rigid ball in various positions. Consider a hemispherical bowl where a rigid ball is rested at the equilibrium position. You can see the equilibrium position is here. Okay. Now, if you slightly disturb the ball, then it will oscillate and then come to rest again at the equilibrium position. Consider this position. Here the hemispherical bowl is shown in such a way that convex side is upward. So, if the ball is at the equilibrium position and slight disturbance of its position lead to the instability. So, this configuration is unstable equilibrium position. Then there is another position, a neutral equilibrium position. Say, consider a plane surface where the ball is placed, and if it is displaced to a certain position, it will remain at the new position. So, this is what is neutral equilibrium position. Now, the buckling is the change of configuration, that is from stable equilibrium position to the unstable equilibrium position, but in between a neutral equilibrium position has to be there. So, stable equilibrium to neutral and then unstable. So, in between stable and unstable, a neutral equilibrium is there, and we have to find this neutral equilibrium position that gives you the critical load of the compression member, and compression member is your maybe your plate or maybe your this column also, because you can see in steel structures, whether it is a column, suppose a column may consist of a box section where the sides of the boxes are plates. So, in that case the plates will buckle according to the manner in which plate buckles takes place. So, suppose for example, the plate girder which has the flange and vertical wave. So, in that case the vertical wave will buckle like a compression member. So, any steel structure if you see, these are composed of plates. So, therefore, the plate buckling is important for the design of steel structures. Okay. Now, we shall try to find out the buckling load of the plate, but before that I want to find out the differential equations of equilibrium considering the in plane forces, because buckling is only possible when there is a application of axial forces, and these axial forces must be compressive. So, we shall today derive a general expression for the differential equation of plate considering the in plane forces in addition to the transverse load. After that I will show some applications, and then buckling can be considered or analyzed with the help of this equation that we will derive today just by changing the sign of the in plane load. Okay. So, and taking the lateral load to be 0, because buckling is always a homogeneous boundary value problem. So, there will be no external load in case of buckling, only the axial forces that is applied in the buckling analysis, and we have to find the value of this axial force as the critical value. Okay. Now, let us see the difference between plate buckling and column buckling. Now, once column has buckled, there is some difference that can be noted very easily, or it can be observed after detailed analysis. So, some of the statements that I have written here are from general observations of the buckling equations of the plate and column, and also there is a note from the research paper. So, research paper, this observation, that is the strength of the plate in the post buckling cases, that I have brought here just to illustrate this, but post buckling behavior is not included in this syllabus. Okay. So, once a column has buckled, it cannot resist additional load. So, that means this axial load that which the column buckles can be taken as a critical load of the column or failure load. Okay. But this is not the case in case of plate. Okay. So, plates supported at the edges or are interconnected to other plate continue to resist additional axial load even after the load reach their buckling values. So, this phenomenon is observed in case of plate. For example, a plate has dimensions which are important in both directions, say x and y direction. So, when the buckling takes place in case of line elements, a column that we have studied, we have seen that the bend shape that is formed is in the form of a single half wave that gives the lowest value of the buckling load, that is the critical load. So, number of half waves can increase when the buckling load also increases, but for the design purpose we take only the lowest load. But in case of plate, it is seen that the buckling load is determined not only by considering the same half waves in both the directions. Okay. So, in that case, in this case of plate buckling, the number of half waves that are necessary for buckling to take place varies in both directions. So, it may happen that for some support conditions, the number of half waves in x direction is say m, but number of half waves in y direction may not be m. So, this may be different. So, that we have to find out by detailed analysis. The additional load that plate resists even after the buckling takes place may be 10 to 15 times higher than the initial elastic buckling load. So, for a plate element, post buckling load is much higher than the initial buckling load. Now, the concept of plate buckling, the critical stress that we find for the plate has been adopted in the design code. I am mentioning the Indian Standard Code of steel design, steel structure, that is IS 800, where the critical stress of the plate that we will find by solving the differential equation has been adopted in the code for checking the buckling resistance of the plate, especially for the plate girder wave. Now, let us discuss the differential equation, that is the most important requirement for solving the buckling problem in our case, because the solution of buckling or bending or even vibration, whatever you consider, can be solved either in a closed form, deriving the closed form expression, or can be solved by taking approximate method. But first let us learn the closed form solution, which will establish the benchmark results, that in some cases we can verify, even the complicated cases when we model the plate with the discrete method like finite difference or finite element, then to check the model results of the discrete methods, we can verify the results of this, or we can compare the results of the closed form expression. So, that is why closed form solutions are necessary in case of mechanics problem. Okay. So, governing differential equation of the plate ignoring the in plane forces can be written, say d del 4 W equal to q. Okay. D is the flexural rigidity of the plate, which is given by E h cube divided by 12 1 minus mu square, where E is the Young's modulus of elasticity, h is the thickness of the plate, and mu is the Poisson ratio. So, D is actually depends on the material properties and the plate thickness. Boundary condition is not influencing the value of D. Okay. Del 4 is a operator which consists of 3 terms, del 4 by del x 4 plus 2 del 4 del x square del y square plus del 4 by del y to the power 4. So, this operator, when we operate with W, you will get the full differential equation of the plate, and Q is the distributed transverse load on the plate, that is shown here. Okay. Now, in this figure you are seeing that the plate is subjected to in plane forces. Okay. So, what are the in plane forces? One is the force Nx, that is the axial force along the x direction, that is acting on a side which is parallel to y axis, there is the Nx, the axial force, and we take here the Nx is uniformly varying or uniform along this direction. So, at x is equal to 0 edge and x is equal to a edge, the in plane forces are denoted by Nx, and y is equal to 0 and y is equal to b edge, the in plane forces are denoted by Ny, and this is also constant, that means uniform along the edges. So, here the along the x axis the length of the plate is a, along the y axis the length of the plate is b, transverse force is q, and we have shown here an element of the plate, not the full plate. So, dx and dy is the element of the plate, but when we consider the equilibrium of the forces that is acting on the plate, especially I am showing here in the free body diagram the in plane forces acting on the element dx and dy, what we got it, this the in plane forces on this face, this Nx into dy, dy is the length of this place, this face or edge. So, total force is Nx into dy. Okay. On the opposite face, this force Nx plus the increment, though increment will be del Nx by del x into dx, and the length of the side is also dy. So, it is multiplied by dy. Okay. So, in the other edges you can see Ny dx is the force, total force acting along the edge y is equal to 0. Similarly, on the edge y is equal to b, you are seeing the in plane force, that is n y plus del n y by del y into dy into dx. This is the in plane force acting along the edge y is equal to b. Okay. Now, there are shear in plane shear forces that gives rise to compressive force in along the one diagonal, and the other diagonal there is a tensile force. So, you can see here, if you take the resultant of these two in plane shear forces, that is acting along the edges tangential to the edges, then you will get the resultant is the tensile force along the diagonal. Similarly, is this case, here you will get the resulting force is tensile. Okay. So, along one diagonal this is tensile force, and other diagonal there will be compressive force. Okay. So, the plate is under the action of in plane direct forces and in plane shear forces. So, in plane forces are actually n x, n y and n x y, and by virtue of the complementary nature of the shear force, n x y equal to n y x. So, that we will take in case of derivation. Okay. Now, here in this figure I have shown only the in plane forces, no other forces are shown, because I want to find out the interrelation between this n x and n x y. Okay. So, if I consider the equilibrium of the forces along the x direction, I can establish a equation of equilibrium. Then if I write the equation of equilibrium, that means resolving the forces along the y direction, then also I will get another equations of equilibrium. So, by doing so, here say along the x direction, what are the forces? One forces is this along the positive direction of the x axis. This force is n x plus del n x into del x into dx into dy. So, that force is written here. Then minus, this is acting in the opposite direction. So, minus n x into dy. So, this force is written here. Then plus other force, let us see in the x direction. Positive direction is this force n x y or n y x plus del n y x by del y into dy into dx. On the opposite direction, n y x into dx equal, this is the force. So, total force I have summed up and equated to 0. Okay. So, now after cancelling some terms, that you will get say n x dy and n x dy, this is n x dy, from here it is positive, and here you are getting minus n x dy as negative quantity. So, this term will get cancelled. Similarly, other terms you will get n y x dx, and here you will get minus n y x dx. So, this term will get also cancelled. So, then after dividing both sides by the area of the elements, that is dx dy, that is not to be treated as 0. So, we ultimately get an equation of equilibrium involving the membrane forces, that is del n x by del x plus del n x y by del y equal to 0. Similarly, summation of forces in y direction gives del n y by del y plus del n x y by del x equal to 0. So, these two forces are the equations of equilibrium in the x and y direction, and this is possible due to membrane action of the plates. So, plate will resist these lateral the axial forces, and this will establish the equilibrium of the forces. Okay. Now, this form can be converted into this equilibrium equation of the two dimensional elasticity problem, that involving the sigma x, sigma y and tau x y, that we are familiar. These three stresses are important in case of plate. Now, if we take a unit width of the plate, then and n x is uniform, then we can write sigma x equal to n x by h. Similarly, we can write sigma y is equal to n y by h, and tau x y we can write n x y by h. So, substituting this n x equal to sigma x into h, n y x equal to tau x y into h, we convert these two equations, say 1 and 2, in the form of say sigma del sigma x by del x plus del tau y x by del y equal to 0, and then another equation this del sigma y divided by del y plus del tau x y by del x equal to 0. So, these two equations are equation of equilibrium in plane stress condition in absence of body forces. Generally, body forces in the axial directions remain absent, and body forces in axial directions generally it is produced due to thermal loading. So, here we neglect this, and therefore, the equilibrium equations in x and y direction we have written, and it is forming the conventional two dimensional equilibrium equation for plate. Okay. Now, we want to bring the stress function concept in this expression. Okay. Now, let us discuss let us introduce the stress strain relationship. Now, strain in the x direction is del u by del x, strain in the y direction is del v by del y, and shear strain is del u by del y plus del v by del x. Okay. Then compatibility condition for the strain can be written as del square epsilon x by del y square plus del square epsilon y by del x square equal to del square gamma x y by del x del y. Okay. So, this is the compatibility condition in two dimensional elasticity problem, and stress strain relationship also known to us. Stress strain relationship is epsilon x equal to 1 by E sigma x minus mu into sigma y, where mu is the Poisson ratio, and then epsilon y equal to 1 by E into sigma y minus mu into sigma x, mu is the Poisson ratio, then gamma x y, this is the shear strain, is tau x y by g, g is the shear modulus of the elasticity. Now, substituting stress strain relationship in compatibility equation. So, compatibility equation is this equation. So, stress strain relationship we substitute here epsilon x, epsilon y and gamma x y we substitute here, then we get this equation. Okay. Del square by del y square sigma x minus mu into sigma y plus del square by del x square sigma y minus mu into sigma x equal to 2 del square tau x y divided by del x del y into 1 plus mu. 1 plus mu is coming here because of the expressing the shear modulus in terms of the Young's modulus of elasticity, and Young's modulus of elasticity appears in both the sides of this equation 8. So, therefore, it get cancelled. So, only we are living with this 1 plus mu. Okay. Now, if I write again the equilibrium equation 3 and 4 that we have derived earlier, here you can see this equilibrium equation in two dimensional elasticity, that is plane stress problem, is again written here del sigma x by del x plus del tau y x by del y equal to 0. This is one equation. Another equation is del sigma y by del y plus del tau x y by del x equal to 0. Okay. So, if I differentiate this first equation, the first equation 3, this is the equation number 3, and second equation, that is this equation. So, if I differentiate first equation with respect to x and second equation with respect to y, and then if I add both the quantities and separate this tau x y terms in one side, then after adding, when you differentiate this expression, okay, when you differentiate this expression, that will be del square sigma x by del x square plus del square tau y x by del y square. If you differentiate this expression with respect to y, then you will get del square sigma y by del y square plus del square tau x y by del x into del y equal to 0. So, then if I add this and keeping this del square tau y x or del square tau x y, this is the same thing. So, del square tau y x by del x del y. So, one mixed derivative term will be coming. So, if I isolate this, that is with the after addition it will be 2 into del square tau x y divided by del x del y equal to minus del square sigma x by del x square minus del square sigma y by del y square. So, this is the relation that has been obtained. How it is obtained? This expression is differentiated with respect to x, this expression is differentiated with respect to y and then added. So, we ultimately arrive at this equation. Okay. Now, this equation, that is I numbered it 9, this equation is now substituted in equation 8. So, substitute equation 9 in equation 8. So, suppose the earlier slide, see this equation 9, now you substitute here, directly you substitute here this equation, then you will get equation like that, del square sigma x by del y square plus del square sigma y by del x square plus del square sigma x by del x square plus del square sigma y by del y square equal to 0. You can note here, that is the derivative of sigma x with respect to y and derivative of sigma x, that is the second derivative with respect to x, both are appearing. Similarly, the derivative of sigma y with respect to x, second derivative, and second derivative of sigma y with respect to y appearing again. So, both are appearing. Derivative of this sigma x is here with respect to y as well as with respect to x. Similarly, derivative of sigma y is with respect to x as well as with respect to y. So, this can be written in a convenient form, say using this operator del square by del x square plus del square by del y square into sigma x by sigma y. This can be written in this form. So, now we are familiar with this operator. This operator is nothing but your Laplacian operator, that is del square. So, we can now write this equilibrium equation, compatibility equation as del square into del x plus sigma x plus sigma y, okay, summation of sigma x plus sigma y. Now, this is a very popular equation in plane stress problem, and then we want to express the eddies, the stresses, the normal stresses and shear stresses in the form of eddy stress function. Because when we solve a equation of the plate simultaneously subjected to in plane forces and this transverse loading, then if we introduce this stress function, then it will be convenient, because earlier we have got the equilibrium equation where it is del n x by del x plus del n x y by del y equal to 0, one equation, and another equation del n y by del y plus del n x y by del y equal to 0. So, these equations we obtained earlier, and we have to find out simultaneously the in plane forces as well as the vertical deflection of the plate also. So, because of this, the bringing the eddy stress function phi in the equation will be convenient. So, the Airy stress function phi is introduced in such a way that second derivative of phi with respect to y will give you this sigma x, and second derivative of phi, that is the stress function with respect to y with respect to x will give you sigma y. You can note here the difference, that when we require the sigma x, we have to differentiate stress function phi with respect to y, second derivative. Then when we require to find sigma y, we have to differentiate this Airy stress function 2 times with respect to x. Then tau x y will be given by this mixed derivative and with a minus sign. Now, introducing this stress function in the compatibility equation, the Airy stress function now can be written as this is del square sigma x plus sigma y. Okay. Now, introducing this, if you add this del square phi by del y square plus del square phi by del x square, then again we can write this is del square phi. So, this equation can be written as del square into del square phi equal to 0. So, this is again a equation of biharmonic nature, a homogeneous equation, very popular equation in plane elasticity problem, and where operator del 4 is expressed as del to the power 4 divided by del x 4 plus 2 del to the power 4 divided by del x square del y square plus del to the power 4 divided by del y to the power 4. So, this operator is similar to our operator that appears in the plate deflection equation, okay, in absence of this in plane forces that we have derived earlier. Okay. Now, the equation that we have obtained is considering the equilibrium of forces in the axial direction, that is the x direction as well as y direction. Now, let us consider the equilibrium of forces in the vertical direction. Vertical direction is the z direction. Again we take an element of the plate of length dx along the x direction and length dy along the y direction. This direction is understood as the x direction along the x axis, and this direction is understood as the direction along the y axis. Okay. So, here for simplicity we have taken these edges, two adjacent edges are fixed. It is not necessary for derivation purpose that one should take these edges are fixed. We are taking these edges as fixed because we are taking the slope, the change of slope at opposite edges, that is measured from a datum which has 0 slope. But it does not matter if the slope is other than 0 here also, that means if this edge is not fixed also, then also the change of slope can be calculated at the opposite edges. But for simplicity of calculation, we have taken these two adjacent edges as the fixed. Okay. Now, let us see the forces that are acting along the edges. On this edge it is n x dy, on the adjacent edges that is fixed, that is n y dx. Membrane shear forces here n y x dx. In this edge membrane shear forces is n x y dy. Okay. Now, let us see what is the condition at the opposite edges. In the opposite edges, if you see here, first let us see along the x direction. You see, due to deflection of the plate, the slope will be changing and as well as curvature will be also generated. Okay. So, here if this is the change of forces, that is the with increment of n x that I have written n x plus del n x by del x into dx into dy. So, that is the incremented n x in the opposite phases, and due to deflection of the plate, this force is now making an angle with the normal to the edge. Okay. Now, this angle is nothing but the change of slope. Okay. So, change of slope, if I take the slope here is del y by del x, and the rate of change of slope will be del by del x derivative del by del x into del w by del x, and this change occurs in a length of dx. So, it is multiplied by dx. So, this is the angle. So, for small deflection this change of slope, because change of slope is net slope here, because here we have clamped this edge. So, therefore, we take this as the slope, that is the angle that the normal to the deflected surface makes with the original x axis that was before the deformation. Okay. So, therefore, if we take this as the angle, then if I want to calculate the vertical component of the forces, then this force, say this force is say P is here n x plus del n x by del x into dx into dy, and this angle is say theta. So, naturally, we will calculate the vertical component of this force is, because we are considering the equilibrium in the vertical direction, that is z direction. So, vertical component of this force will be say p into sin theta. P is this term, complete term, and theta is this del square w del x square into dx. Although I have not written here, but say for convenience take this angle as theta. This is understood as a angle, and for small deflection sin theta equal to theta. So, generally you will get the vertical component of this force as n x plus del n x by del x into dx into dy into del square w del x square into dx. Similarly, on the other edge, because here the edges are clamped, so there will be no slope here. So, naturally the vertical component of these two forces are 0. Similarly, vertical component of the shear force along these edges, clamped edges, will be 0. Now, consider the axial forces, that is N y, on the other direction, that is the along the edge, opposite edge, that we have considered first here N y dx, along the edge dx. Now, here we are considering this incremented force N y plus del N y del y into dy into dx. So, in a similar fashion, now we can calculate the change of angle, that is the angle here, that is the slope, because here we clamped it. So, del square w by del y square into del y. So, the intention of clamping the edges here only to get the change of slope as something minus 0, that for convenience of calculation, no other purpose. Okay. So, del square w by del y square into dy is the slope here, that is the angle, and vertical component of this incremented force N y plus del N y del y into dy will be into dx will be this force multiplied by sin theta. Theta is this angle. So, this angle is again for small theta, this will represent as sin theta equal to theta. Okay. So, for membrane shear forces also we are getting the vertical component. So, this is the rate of change of angle of twist that you are getting here, del square w del x del y into del x, and because these edges are fixed. So, we are getting this angle as the slope angle. So, the vertical component of n x y is also found out by resolving the forces in the vertical direction, and this vertical component of this shear will be n x y plus del n x y by del x into dx dy into del square w by del x del y into dx. Similarly, here vertical component of the shear force will be n y x plus del n y x by del y into dx. So, these vertical components are known. Now, we can sum up the forces in the vertical direction. Okay. So, summing up the forces in the vertical direction, we can write now, this is one vertical component of this that we have written here, then vertical component of this force we have written here, then vertical component of membrane force we have written here, vertical component of membrane shear force here we have written here, and since these edges are fixed, so there will be no vertical component. So, the summation is some force say Fz. Okay. So, after cancelling some common term, you will get some common term and neglecting the square of the small term, because here you will get, suppose if you multiply term by term, then in the first expression you will get dx square term here, del nx by del x into dx square into dy del square w del x square. So, when the square of the small quantity comes, then we should neglect it, because we are considering the small deformation theory. Okay. So, considering the equilibrium in the z direction and dividing both sides by dx dy and neglecting the square of the small terms, we get this equation in this form: nx del square w by del x square plus 2 nxy del square w by del x del y plus ny del square w by del y square equal to p star xy. P star is a lateral load produced by the in-plane forces. So, that force we have taken as a fictitious load on the plate. Okay. Thus, the effect of membrane forces on the deflection of the plate is equivalent to a fictitious lateral load. Thus, adding P star is a fictitious adding load, which is nothing but nx del square w by del x square plus 2 nxy del square w by del x del y plus ny del square w by del y square equal to P star. So, adding this P star to the plate equation, now we get the plate equation in this form: d del 4 w equal to q x y plus nx del square w by del x square plus 2 nxy del square w by del x del y plus ny del square w by del y square. If the plate has initial curvature, sometimes plate may have even like column, the initial imperfection is also common in many cases. So, if initial curvature is there, say in the form of w naught, it may be a continuous function or it may be some localized imperfection also. Then we can add this to the this w and we get this equation, say d del 4 w equal to q x y nx and then del square w naught plus w by del x square plus ny del square into w naught plus w by del y square plus 2 nxy into del square into del w naught plus w divided by del x del y. W naught is the initial imperfection or initial curvature or initial deflection of the plate. Now, introducing the Airy's stress function that we have earlier obtained. What was the Airy's stress function? Airy's stress function was that sigma x phi is the Airy's stress function and phi is such that del square phi by del y square is your nx sigma x, and similarly del square phi by del x square is sigma y, and minus del square phi by del x del y is tau x y. So, introducing this quantity, now we can write this equation, the plate equation, in presence of the transverse load as well as the in plane forces, like that d by h, h is the thickness of the plate, del 4 is the operator, biharmonic operator that consists of 3 terms. The terms are del 4 by del x 4 plus 2 del 4 by del x square del y square plus del 4 by del y to the power 4 equal to q by h, q is the distributed load, plus del square phi del y square del square w by del x square minus 2 del square phi by del x del y del square w del x del y plus del square phi by del x square into del square w by del y square. This is coming due to conversion of n x in terms of this stress function, because n x is related to sigma x and sigma x is related by the second derivative of the Airy stress function. So, if in plane forces are not known, sometimes in plane forces are not known, then additional differential equation connecting lateral displacement and Airy stress function is used. So, that is the additional deflection that we have used. So, in that case solution has to be obtained by iterative technique. No closed form solution may not be possible in that case. Okay. If we want to study the buckling phenomenon of the plate, that is our intention. So, first we have derived the differential equation of the plate subjected to in plane forces. Okay. So, this is the differential equation of the plate subjected to the in plane forces. Now, when we study the buckling, buckling is a homogeneous problem. So, where q should be absent. So, we shall put q equal to 0 and then the sign of n x, n x y and n y will be reversed to produce the effect of compression on the plate. So, if it is reversed, the sign of this n x, n x y and n y are reversed and q is taken to be 0, then the equation for buckling of the plate is given by this: del 4 w plus n x by d del square w by del x square plus n y by d del square w by del y square plus 2 n x y by d del square w by del x del y equal to 0. Okay. Now, let us consider a problem, illustrate a problem. We have taken a simply supported plate, all edges are simply supported as seen in this figure, and it is subjected to transverse load q as well as this axial compression here n naught. So, n naught is the compressive force, but for the time being we will take it as a tensile force, because we have now just derived the equation of equilibrium with the tensile. When we consider the buckling of the plate, then we will consider this n naught as compression, but here we consider the S force as the tensile force. So, if it is a tensile force, then the differential equation is this: d del 4 w equal to q plus n naught del square w by del x square. Now, you can take here a Navier series, because the plate is simply supported along all edges. So, a double trigonometrical series will satisfy the H condition, that is the deflection and bending moment at edges x is equal to 0 and x is equal to a and y is equal to 0 and y is equal to b will be satisfied by taking the double trigonometrical series sin m pi x by a sin n pi y by b with coefficient a m n. So, this double sum can be expanded and the series can be computed for different number of terms. Now, here we are taking this membrane shear force and the other in plane forces in the y direction to be 0, and this force in the x direction is taken as constant, which is n naught. So, differential equation now becomes this. Okay. So, assume a Navier's solution method, we substitute the series in the differential equation and then we get this. If I substitute this series in this differential equation, then in the left hand side we will get this term and in the right hand side we will get this term. Now, multiply both sides by sin m dash pi x by a and sin n dash pi y by b and then integrate in the domain of the plate. So, integration is done in the domain of the plate, and due to orthogonality condition, the sin square m pi x by a dx integration will be a by 2 and another integration of 0 to b sin square n pi y by b will be b by 2. So, this term is this. So, therefore, we arrive at the value of a m n is this, and hence q m n can be written as this expression as q x y sin m pi x by a sin n pi y by b dx dy. For uniform loading, q has been obtained in earlier cases also. So, we get q m n as q q into 4 AB amn pi square divided by amn pi square, where m and n are odd integers. So, if I take q as the uniform load, then q can be taken outside the integral sign and these two terms can be integrated, and after substitution of limit, lower limit and upper limit, you will find that the value of integral exists only for odd integers. There is odd value of m and n 1, 3, 5 up to infinity. Okay. So, this amn is found, and after finding the amn, we can now write down the deflected shape. So, deflected shape we have taken this, and amn is known after finding this series solution, and then the complete deflection surface is written like that. Okay. So, maximum deflection occurs at the center, and therefore, by substituting x is equal to a by 2 and y is equal to b by 2, and for odd value of integers we get this maximum deflection as this value. You can see in presence of axial tension, the maximum deflection reduces. So, the maximum bending moment will also get reduced. Okay. So, an exercise can be solved. A rectangular plate A cross B carries a concentrated load at the center. It carries also axial tension N along x direction at the edges x is equal to 0 and x is equal to a. Calculate the following. We take m is equal to 1, n is equal to 1, deflection at the center, then bending moment at the center, and shearing force and twisting moment at a by 4 by a by 4 by b by 4. Okay. So, let me give some steps of this exercise and you can complete this and get the results. So, I am discussing now a problem where I have taken a rectangular plate side A and B. A is along x axis and B is along y axis. Okay. It carries a concentrated load at the center. Say center coordinate is a by 2 and b by 2. I have taken the origin at O, and also it is subjected to in-plane forces uniformly distributed along the edges. Okay. So, now the differential equation of the plate can be written as plus n naught divided by d del square w del x square. Other terms will be absent because there is no other in plane forces, equal to q x y. Okay. By d. Okay. Now, you can see here the load is this concentrated load, not the distributed load, but we know that concentrated load can be expressed in the equivalent distributed load by making use of direct delta function. So, here I can write q x y, because it is, suppose the concentrated load is acting at any point along any plate whose coordinate is say xi and eta, okay, measured with respect to origin, then we can write okay. So, q x y we can express like that. So, therefore, the expression q m n that is required to find out is nothing but the double integral 0 to a 0 to b, and instead of q x y we now write this p I can take outside and delta x minus xi delta y minus eta and the function sine, because we are taking first term. So, let m is equal to n is equal to 1. So, sine pi x by a sine pi y by b dx dy. So, this integral can be easily evaluated and it forms that p sin pi xi by a sin pi eta by b. I have taken a general coordinate xi and eta, but in the final result you can put xi is equal to a by 2 and eta equal to b by 2. Okay. Now, once the qmn is found, then we can find the amn. Okay. Now, here of course, the amn will be your this first term consisting of only the first term of the series. So, m is equal to 1, n is equal to 1. Okay. So, now if I write the expression of this A11 will be, because m is equal to 1 and n is equal to 1, A11 will be 4 p sin pi xi by a sin pi eta by b divided by the terms that contain the blade parameters, say pi square a square plus pi square b square whole thing square. Then it will contain the effect of axial forces n naught pi square d a square a b d. Okay. So, this is your A11. So, once you find the coefficient of deflection, that only one term is needed. So, there is no difficulty to find the deflection for the center deflection. Now, center deflection term is written here, w x y is a function of this A11 into sin pi x by a sin pi y by b. Okay. So, once you get this, then at center x is equal to a by 2, y is equal to b by 2, and also p x at center so xi is equal to a by 2 and eta is equal to b by 2. So, maximum deflection that you get is at the center and its value is 4 p divided by pi square by a square plus pi square by b square whole thing square plus n naught pi square by d a square a b into d. So, this is the value of the maximum deflection that we require to find. Now, you can see in presence of axial tension the maximum deflection decreases. Now, once you get this maximum deflection, then the deflection expression, then you can proceed to find the bending moment and shear force also. Okay. Now, let us find what will be the bending moment and shear force at any point x y. Okay. If you see the expression for bending moment, the bending moment in x direction is nothing but minus d del square w del x square plus mu into del square w del y square, and bending moment in y direction will be minus d del square w del y square plus mu into del square w del x square. Now, since the expression for w is known, w is A11 that we have found, and sin pi x by a sin pi y by b, we can calculate this quantity without any difficulty, because only in that case you have to substitute the second derivative of this expression. So, now the twisting moment m x y is calculated as minus d 1 minus nu del square w del x del y, and shear force say Qx at any point can be calculated d del by del x del square w, and Qy is calculated minus d del by del y del square w. Okay. So, once the w is found, then other quantity can be easily calculated. So, as an exercise you can complete this. So, this type of problem you may get in the assignment. So, there I will get the complete solution. Okay. So, what we learned today? Today we have learned the differential equations of bending of plate subjected to in-plane forces, which we neglect earlier. Now, here we consider the in-plane forces and obtain the differential equations of the plate, and then we discuss the concept of buckling, because this equation will be used in case of buckling also, reversing the sign of these in-plane forces. Then we have solved some problems to illustrate the use of this equation. Thank you very much.